Let's start with
So we're very happy to have Julian Sonner. Julian, who is PhD at the University of Cambridge, then remained there for a little while longer before crossing the pond to the other Cambridge. He was here for a postdoc at MIT, and then returned to Europe to become a faculty at the University of Geneva. I should also mention that Julian will be here for a while, so anyone that's interested to talk to him should just come and find him at Jefferson. He'll be here until the end of summer, if I'm correct. And he works on the interface of string theory, holography, and condensed matter physics, which often find sort of a connection in quantum chaos, in which he is an expert. And today, indeed, he will tell us about thinking about gravity and chaotic times. And I'm sure he'll tell us if that's a joke or not.
All right, hold your horses. Okay, thanks. So thanks, Vito. Thanks for the invitation, and thanks everybody for coming. It's a pleasure to be here. So I was told that this is a diverse audience, so this is not a talk to the experts. So I see that there are many experts, so I'm sorry if I bore you a little bit. But actually tomorrow I'm giving a talk at MIT, 2 stops down the T, which will be on a very similar topic, but will be much more technical. So if you actually have questions, of course, I'm always happy to talk about them in person, but also tomorrow there'll be a more sort of technical seminar on a similar topic. So let me start with an introduction. So this is the Black Hole Initiative. I really don't need to tell anyone here that this is a subject that used to be very theoretical and sort of perhaps far removed from what people thought was measurable. But as you know, and as many of you in fact even established, black holes are definitely real. We can show them, we can see them, we can image them, for example, the center of our galaxy or in another nearby galaxy. And so the fact that these black holes really exist, to me, kind of just reinforces even more that we need to understand them, that we need to understand their properties. But that's, of course, famously a large challenge. So these black holes from a classical perspective are extremely simple. They're arguably the simplest solutions that Einstein's equations allow. But arguably, nevertheless, they are also at the same time the most puzzling objects that we know to exist in the known universe. And one of the the starting points for their puzzling behavior is precisely this observation due to Bekenstein and Hawking that black holes, if you open your point of view a little bit further and you take into account semi-classical contributions, actually seem to behave like thermodynamic objects or thermodynamic ensembles. So they have an entropy, which famously in all the glorious units is given by the area of their event horizon, not the volume of the black hole, the volume that is occupied by the black hole. And they have an associated temperature, the famous Hawking temperature, which also here for a Schwarzschild black hole, I've given you inversely with the mass. And you have all the other parameters that kind of show that it unifies all the areas of theoretical physics that one might ever be interested in. So the question is, what do we make of this thermodynamic behavior? And how should we think about it? Does it give us the right kind of clues to understand the underlying microstructure of these objects? So the slightly more detailed question then that I'm going to just touch upon today, and just maybe talk about some small aspect of it, is that typically when faced with such a macroscopic thermodynamic system, we like to understand it microscopically. And so this macroscopic black hole should somehow be accounted for by a number of microstates, black hole microstates, which poetically might be like the atoms of space-time, which is why I put these symbols of atoms here. And they should account for the macroscopic entropy. So for example, we should understand the Bekenstein-Hawking entropy itself, BH, which for an object, a black hole now in natural units with a compact horizon is famously a finite number, by accounting for it with a certain number of microstates that agree with the counting. So the log of the number of microstates should agree with this Bekenstein-Hawking entropy. But of course, actually using string theory very famously for a number of interesting black holes, one can actually account for these microstates, the number of them, as has been also done by people in this room. However, as I'm trying to suggest here, the things that we've been thinking about in recent years concern sort of other detailed aspects of these microstates. In particular, what is the microstructure of the Hilbert space of these black hole microstates? In other words, how do they arrange themselves, and how do we use them to think, for example, about dynamics of the black hole? So what do we learn about the microstructure of the Hilbert space of the black hole? And perhaps also, do we learn more lessons about the gravity, microstructure more generally? All right. So as I guess Evita already suggested, the tool that I want to use is essentially chaos. And why? Because very generally in physics, if we have a thermal state, we know that, or at least in all well-understood examples, we know that the way that this thermality actually arises is via chaotic dynamics. So we find that thermal states are very simple. They are specified only by a few parameters, like something like temperature or pressure or certain other macroscopic thermodynamic variables. But in fact, at the same time, the underlying microscopics, the dynamics, is incredibly complicated. And in fact, in theories that show this property of thermalization, meaning that some generic initial excited state actually evolves to one of these simple thermal states, is the dynamics of chaos, both classically and quantum mechanically. So in that sense, chaotic dynamics is a very effective randomizer, but randomizer in the sense that random states on average look extremely simple. So it drives the system to this emergent simplicity. And one example that we all see pretty much every day is, for example, if you have your coffee in the morning and you put a little bit of cream in there or milk or whatever you prefer, and you just let it come to equilibrium, there will be incredibly complicated dynamics. There'll be, in this case, even turbulent dynamics. There'll be convection. There'll be, heat exchange and so on. But in the end, you get the end state of a cup of coffee or maybe a cup of tea here, which is perfectly mixed, which has the same concentration of milk and tea or milk and coffee everywhere, which has a homogeneous temperature, and which is in thermodynamic equilibrium. So this very complicated dynamics has a tendency to drive to this simple emergent state. So that's essentially the motivation to say that in order to understand the apparent simplicity of the black hole, we should think about the chaotic dynamics that underlies it. But just as a side remark, it is also an interesting question. In fact, I earlier had some already a brief chat with Mehmeta about this. There is also an interesting ongoing effort to understand how effective this randomization actually is. So can you use this chaotic dynamics, for example, to engineer systems that are chaotic, sufficiently chaotic in a specific sense, quantitative sense? So for example, can it mimic what people call unitary K designs? So, right, so much for the motivation. Now let me talk about these time scales. So again, this is still in the spirit of giving you a bit of a background. So here, let's think about some background related to how chaos works and how it might leave signatures that could be interesting for us. So I'm repeating here this mantra, which is that black holes are thermal states. And so it would be interesting to understand thermalization in the sense that I just evoked in gravity. Now, in classical mechanics, that's actually a beautiful and well-developed subject. So we typically look at phase space. Of course, we want it to be more than two-dimensional, but I drew it anyway in 2 dimensions. And what happens is that you have some initial phase space distribution, and because of basically the fact that trajectories that initially start nearby, they exponentially have a tendency to diverge, which goes under the name of Lyapunov. You actually get precisely this effect of the T, namely that the dynamics will be mixing and ergodic, and basically mimicking the thermodynamic ensemble at large times. And there are, as a whole mathematical theory of how this works, it is well established. So basically in classical mechanics, there is a clear connection between nonlinear instabilities of chaotic systems and the way that this cup of tea becomes a homogeneous state. Now in quantum mechanics, it's less well understood, and it's also on the face of it a very different kind of mechanism. So in quantum mechanics, of course, we shouldn't talk about trajectories. That doesn't make any sense. And also, well, we can kind of do quantum mechanics on phase space, but it's also not really natively how we usually talk about quantum mechanics. So these concepts don't immediately lend themselves to understanding chaotic dynamics and thermalization in quantum systems. That's, of course, what we eventually want to do. So let's talk a little bit about how it happens in the quantum context. So in the quantum mechanical context, already it is an interesting question to see how do we actually characterize a system that is chaotic. And we characterize it by not because we understand, let's say, the whole chaotic hierarchy as we do in classical systems, but we understand it by having sort of very, let's say, telltale signatures of quantum systems that behave chaotically. So for example, if we follow the evolution in time of such a system, for example, as it approaches the thermal state, then the earliest time scale, so first of all, I already put some 3-letter acronyms here. So I'm saying that nowadays, the way that we understand it in quantum mechanics goes through ETH and RMT, which stand for the eigenstate thermalization hypothesis and random matrix theory. But more about this in a minute. But the earliest timescale, which I didn't even bother writing here, is what people like to call the local thermalization scale, which basically scales with the inverse temperature. That's when locally correlation functions start to behave as if you took them with respect to the thermal density matrix. But more of value for black holes, or at least the discussion today, is the timescales that I'm talking about here. So you have a timescale which goes logarithmic with the number of degrees of freedom of the system, the so-called scrambling timescale, which tells you actually something that can be argued to be analogous to something like a Lyapunov exponent. It has to do with the sensitivity of quantum evolution to changing initial conditions. That is sort of the earliest timescale that one discusses in this context. Much later, and for example, in systems that will connect to black holes, is something that's called the Thouless timescale. So you see this already scales polynomially with the entropy, at least in the systems that we were able to analyze. And that's a system, that's a timescale in which the system will start behaving in a sense that I'll specify on the next slide, as if it were a randomly sampled matrix.
Can I ask a basic question? Classically, there are these two sort of notions of chaos. One of them is initial condition sensitivity, the Lyapunov kind of separations, right? And then there's fractal kind of chaos. How do these translate in the quantum domain? Or when you go to the quantum domain, is this the quantum analog of the Lyapunov kind of sensitivity?
This, I would argue, is,
Uh-huh.
yes. And the fractal one, I mean, I'm not sure there is a good connection to the classical notion of fractals that you talk to me about, but actually there is some fractality in certain systems. So what we're talking about here is actually something that has to do with the eigenstates of the system.
Mhm.
And these eigenstates of the system, they can have some fractal nature in
I
certain
see.
systems, but I don't think it's very generic. And I'm also not aware that that relates to your classical notion of fractals. But yeah, I can't really remember off the top of my head now, but there are some fractal, yeah, there are some stories there. I can look them up and tell you about them now. But this is very much related to the classical notion of Lyapunov. So at this time scale, basically the system, this is sort of like the time scale at which we can start to talk about chaotic signatures in the microstates of the system. And that's why we're going to be interested in those kind of time scales. And let's say the very latest time scale that I'm putting here is one where the system has actually evolved for a very, very large time, a time that is 1 over the average spacing between energy levels. And by the way, this is why I insisted in the introductory slide that the Hilbert space of the black hole is finite. So that means that there is a discrete number of levels. So this thing is well defined. This is kind of the largest timescale that you can talk about sensibly without having to really know the individual microstates. So this timescale is extremely revelatory if you're interested in the microscopic structure of your system, because the signatures of chaos here are really smoking gun signatures of the discrete nature of the microstates. So
Maybe I'm not allowed to ask this question, but
probably not.
Cloudless time means that it behaves like a Gaussian random matrix or like single random matrix. Is that the point?
There are some people who want to define it that way. I'm not among those people, and I think you're not either. I mean, given one or two papers we wrote.
Well, I'm not sure what's supposed to be the definition of the word.
I think that no, I think you're not allowed to ask a question now because it would be a long excursion. But to just give you the answer, I would say that in this sigma model description of systems that we worked out, this is the shortest time at which the zero mode dominates the physics. But I guess it's a detailed answer, and we can talk about it in more detail.
Okay, thanks.
Ahmed.
So as time goes on in the quantum,
Yeah, and it does.
do you like lose information or do you like gain information? Like, can you like in a thermal system, as time goes on, you kind of like, if you coarse grain, you like the system looks more and more thermal. But so now you're saying that here, as time goes on, you can like actually discern more and more of the microscopic. But not by the Heisenberg time.
Yeah, that's very interesting point. I hadn't actually thought about it that way. So typically, of course, we think that you lose information because, as I was saying, it drives really to these simple states. But what I'm talking about here are quantum fluctuations, which typically you don't measure, right? I mean, this is not something that, for example, in this quantum T, I would be measuring. But what I'm saying is that these quantum fluctuations, which are the kind of things that we do talk about in black hole physics, they do reveal information about the microstates indeed. So, yeah, and
I just didn't understand how the last one is being defined. So we start out with a system with a Hamiltonian, and it has some level space.
That's right.
Which is put in at the beginning. Right.
It's a property of the system, let's say.
It's a property of the system.
Yeah.
But this is a property of the time evolution. So.
Right.
So what happens at TH? Because that was true from the beginning, the level spacing.
Correct. So
The last time scale.
yeah. For example,
Okay.
if you look at probes, there can be different kind of probes. One particularly clean probe is the spectral form factor, which is actually what I skipped here, which you can think of as like two copies of the partition function analytically continued. So now it has like the usual kind of Boltzmann behavior, but it also has differences of energy levels conjugate to time evolution. And this thing actually has a very characteristic form, and it shows at the Heisenberg time, there's like a rising behavior at the Heisenberg time. This thing becomes, if you average it, constant. And this constant is an imprint of the fact that the levels really are discrete. Okay, and so any quantum chaotic system, black holes actually included, although that wasn't known until recently, and at the Heisenberg time has this characteristic transition. And if you see this transition from the chaotic dynamics, then you see something, then you conclude that you have enough resolution to see, well, not quite individual microstates, but you see, you know that the microstates have to be discrete. So the discreteness of the microstates at the Heisenberg scale gives telltale signatures in a number of quantities, the cleanest one being the spectral form factor. Right.
So
Good.
are all three of those timescales probed by the spectral form factor?
No, so the scrambling timescale is not well probed by the spectral form factor, but the tau-less timescale is. Yeah. Although I've seen papers that also talk about scrambling of within the spectral form factor, but not to my the best of my knowledge. It's not visible. Yeah, again, because the way that you probe, yeah, I would say that the spectral form factor is something that really tells you about the spectrum. It's a very quantum thing. Like in a quantum system, we should talk about the spectrum of energy levels. That's the most natural thing. The scrambling time is something that is kind of tied to classical notions like Lyapunov, and you actually have to use different observables. And here you use these so-called out-of-time order correlation functions, and the spectral form factor is not one of those. Okay, so drawing back to the general discussion. So now we have these time scales, well, okay, there is various philosophies. One is we want to see these timescales in black holes. The other one is we want to use these timescales to learn something about black holes. But I'll have a slide about this. Now, I already anticipated this because Andy asked the corresponding question. So in some sense, this chaotic dynamics, following the chaotic dynamics, is like a quantum microscope, and it's in this particular sense. This is, of course, also true if you look at correlation functions, because also correlation functions have phase factors that go around all over the place that look like this. But the cleanest is if you just forget for now about operator matrix elements, which only make things complicated, and you look at purely the behavior of these phase factors. And one of the probes that expresses this the most cleanly is this so-called spectral form factor. And the fact that the longer you evolve in time, the more you get sensitive to the differences of energy levels. That's Ahmed, by the way, also partly your question, means that this is sort of like a Fourier microscope as a function of time that tells you more and more about the microstructure of the states. So, okay, this is just a remark. Typically, this level spacing is a non-perturbative quantity. So if we actually learn about the physics around these timescales, we learn about the non-perturbative physics associated to, well, in our case, the Blackwell Hilbert space, but of course, this is also true for other chaotic quantum systems. All right. Now, so one of the ways that chaos manifests itself is via the so-called chaotic level correlations. And that's the statement that if you're able to look at nearby levels, a system that is chaotic will show the same statistical distribution of energy levels as if you had sampled its Hamiltonian from a random distribution of such matrices. So this is like a generalization of random variables. It's just random matrices. Of course, they should be Hermitian, and they might have other symmetry properties. And just like you characterize a classical system that's chaotic by a non-zero Lyapunov exponent, here you characterize a quantum system that's chaotic in terms of particular distributions of random matrices. And so, for example, if you look at the correlation of nearby levels in a quantum system, these should be given by sampling from a Wigner ensemble of matrices. And this was, of course, Daniel's question. Nowadays, we understand that there is more structure here. So this is actually something which is Gaussian, but there is more to that, as Daniel was pre-shadowing. One aspect, so we already discussed the spectral form factor. So let me explain the graphs nevertheless. So we have this black graph, which is the one that the system follows, and we have the purple one, which approximates it at very late times. So the idea is that if you look at the spectral form factor, from the tauless time onwards, these two track each other, and that's precisely the time scale at which I am allowed to treat the system as if it were a random matrix. So if you ask, why is there a random matrix type physics that comes out of black holes, which you have probably read in recent times a lot, one of the ways of explaining is that if you're interested in time scales post-taulas time or in energy scales inversely related to it, then that's basically a feature of a chaotic system. And now the question is, how do you see those level correlations in gravity? And it turns out that that is this famous story that Euclidean wormholes basically give you these level correlations. Now, but the question that I'm going to be talking about more today is one that has to do with the fluctuations. So here, I'm showing you in some sense the average behavior. If I average over these random matrices, that is meaningful and can be diagnosed by these wormholes, but you might also want to know something about the fluctuations. In fact, not just you might, I think you should. So that's what I want to talk about in the latter half of my talk, but I still want to give you a little bit further of an overview. So what I want to say, so what I said right now, I mean, I used often the language of black holes and so on, but those were kind of signature telltale signals of quantum chaos that also are visible in other systems. So what is interesting, what has happened over the last few years, is that people have identified the avatars of this behavior in black hole physics. And so a key number of let's say, states here, what do I want to say, waypoints, is that you can actually get some characteristic physics of gravity out of this. Those who are not experts on ADS-CFT, ignore the word dual for a second. I will get back to it after. So actually, the timescale that I kind of hid, I mean, it is also of interest. This local thermalization timescale is actually the timescale it takes for, let's say, the apparent horizon to form in black hole collapse. And this has been elucidated over the years with some very early papers and some papers that are more recent. So we should think of the formation of this classical apparent horizon as being the signature of local thermal equilibrium. But as you saw, there is still space for a lot of other signatures. So what are these other signatures? The first one, the scrambling signature, actually turns out to be related to shockwave scattering in gravity. And basically encodes or is in some sense the quantum chaotic explanation for this large blue shift of an infalling observer into a black hole. And it has been elucidated by these authors following from work in the 80s, I believe, by Dre and Toft. And the largest timescales that we talked about, so both the taulas timescale and the Heisenberg scale, basically gave this beautiful story of a link between Euclidean wormholes and, well, people also call this, by the way, post-taulas physics as the quantum ergodic regime. So there is a relation between this quantum ergodic regime and wormholes.
So does the scrambling, the shockwave scattering, can happen in other kinds of compact objects or only black holes with horizons?
That's a nice question. And the thing is actually that there is a bound. So this scrambling, it can happen, but there is a bound which actually comes from unitarity and analyticity. And this bound happens to be saturated by the black hole. And we don't actually believe that there are too many other systems that can saturate it. So it's like a particularly extreme form of it. And in fact, in some sense, the red thread through this work that we've been doing is that at each stage, the black hole somehow seems to be the most extreme manifestation of this chaos. It's always the best or the worst at whatever property you have here.
Sorry, it's not for a generic black hole, this is for Schwarzschild specifically.
Well,
Or I think you can do it for a black hole that has an exactly stationary horizon. But I think if you have a highly dynamical black hole, I don't think we think any of this is really true.
well, but I mean, the exponent itself is a property of the equilibrium state, so you don't want to ask about a dynamical one.
Right, I agree. I'm just saying not all black holes necessarily have to equilibrate. We don't have a proof that in ABS, for example. Like Shiraz's gray galaxy story suggests otherwise.
Let's see. I mean, okay, I would still want to argue that generically, the end state is full thermal equilibrium. I think the fact that the generic initial state, that has a trapped surface will form a black hole is also true.
That's true either necessarily.
Well, okay, let's talk about that. But what certainly is true.
If a black hole couldn't scramble the maximal rate, and then you threw something in it, could scramble.
What I'm saying is that I think a lot of the questions about, for me at least, a lot of the issues, genericity of black hole thermalization, have been called into question by this gray galaxy story, which is a late time system that is fairly typical and does not look like a black hole in AES.
I don't know. I mean, one thing that I can say is that in this story, of course, the horizon formation is just the start. So these other stages, the system would still go through these stages. Even Shiraz's gray galaxies would go through these stages. And so the initial state, the end state would be a perfectly thermal state. I mean, at least a generic system, it will thermalize. I mean,
I agree with that.
Yeah.
That's a boundary statement. I agree with that statement.
Yeah. So something that I talked about at last year's BHINL conference, but which I decided not to focus on today because I hope, I assume you all retain all the information from that talk, was that actually a very ambitious goal that we've been pursuing with some collaborators that are here is you can actually take, here we're talking about interesting signatures using it as this microscope, but you can actually take chaos as the foundational principle to build a theory of gravity. And in low dimensions, like 2 and 3 dimensions, this actually seems to work. And that's something that's quite exciting, but that's not the aspect I want to talk about now today. But of course, feel free to talk to me about it. I'm Justin Jefferson for this semester. So what I actually want to talk about is like a new regime, which we identified recently with Herman Velinde in Princeton and my graduate student Pietro Pelliconi, and we call this regime a mesoscopic regime. And so now I'm going to tell you, like, in some sense, I'm adding another bullet point here, and I'm going to enter into like a phase of my talk where I talk about slightly more technical details, but I also want to emphasize I'm kind of adding, one more bullet point. There is a much bigger story, I encourage you to come always and talk to me about what that bigger story is. So I'll remind you of something very, very, so what we want to try and get to is still talk about these fluctuations. I said we should be interested in these fluctuations. Is there some way that we can talk about these fluctuations without actually having to know the full microscopics of the system? And so let me remind you of something from undergraduate physics, which is the idea of Brownian motion. So if you have a particle that's suspended in a fluid, then it's being constantly bombarded by the molecules of that fluid. And so there's this animation on Wikipedia. I think it's actually a simulation. You have this particle, which is larger than the microscopics, but it's also not macroscopic. It's still affected by the microscopic. It's between the scales. And that's why the physicists who were still thinking about Greek at the time call it mesoscopic, between the two. So the idea is that such a particle, if you actually, if you look at the suspension of such particles over long time scales, you just get diffusion. Its position is proportional to the diffusion constant times the square root of the time. And the diffusion constant is related to temperature times some viscosity constant gamma. But it was understood by Einstein, Smoluchowski, and others that the reason for this diffusion law is actually microscopic, namely that the particle undergoes over a mesoscopic scale an extremely large number of molecular collisions. And so there is actually an intermediate description of this, which doesn't solve the quantum mechanics of the whole system and all the molecular states, but instead describes the particle's position as a stochastic process. And in this stochastic process, we should think of the position of the particle as being effectively a random variable, which evolves under a stochastic law, such that it's basically viscous motion, so it comes to a rest with a characteristic exponent e to the minus gamma t. But if you look at the details of the trajectory, you see here, the trajectory is quite erratic. But we know that there are all these molecules that are actually impinging on it. You can characterize it by looking at the expectation, for example, of the two-point function of the velocity with respect to the stochastic process. So that's to say that there is a regime where the probe, the thing that we observe, we don't actually see these collisions. We should only be imagining that we can measure the path of this particle. But there is still imprints of the full microscopics on the system because the particle now has become subject to a stochastic evolution law, and the stochastic evolution law allows you to calculate moments of the position, moments of the signal. And these moments are basically the microscopic fluctuations. And very famously, Einstein and others used this to argue for the existence and the scale of atoms and molecules themselves from observations in which no atoms and no molecules are actually seen. Yeah.
The previous slide, the expectation of n squared that scales like t, so the particle keeps kind of like moving away, but the expectation of v dies off at
yeah, because it's viscous motion, right? So it's viscous motion, but the particle doesn't come to a rest because it keeps being buffeted around. But its average position is proportional to square root of t. So, right, so I would like to pursue an analogous regime in quantum gravity. And so now we go back to a microscopic state. We think about some low energy observer who might measure some correlation function as a function of time. So in the formulation of gravity, this holographic formulation that I will employ, that's sort of the most natural thing that you could think about. And I will argue to you that I can actually think of this G as a stochastic process. And by the way, I deliberated a bit whether I should call this here V0 or G0. I didn't call it G0 because then you would think it's the zero beta infinite temperature. It's not, it's just a constant. It's just a constant that we can also determine. But it gives an insight about, so this regime will give us an insight about the quantum fluctuations, and it also gives us an insight into what one might call this unreasonable effectiveness of semi-classical path integers in gravity. So it's some intermediate scale. So in order to do it, I will retreat to this sort of technically safe laboratory of holographic duality. So let me briefly tell you what that's about. I assume that many of you have heard about it, but nevertheless, let me just say what it is. So we look at gravitational dynamics on a particular kind of space-time. This space-time is called anti-de Sitter space. It's essentially a Lorentzian version of hyperbolic space. So here we have the hyperbolic plane. What this is saying is that let's take the idea that the black hole has an entropy and the number of degrees of freedom that scales with its volume to be a general principle. And let's describe a region of asymptotically alias space-time by putting the microscopic theory that describes it on its boundary, the so-called alias boundary, the red thing here. The gravitational theory is on the interior, which is the interior of this disk. And the theory that lives on the boundary in this particular case has to be a specific kind of field theory, a conformal field theory, or a CFT. So what we're going to do is we're going to construct some mesoscopic description of chaotic boundary CFTs, and we're going to use it to say something about these fluctuations. Now, the natural thing to probe in this setup are correlation functions of operators. And you can have correlation functions with operators whose insertion points are anywhere, but it will be most convenient to talk about insertion points that are on the boundary. And so basically you shake the boundary and you observe what comes back as a function of separation, both in space and time, on the boundary. Okay, so now let's focus on a simple kind of observable. This is this G, whose mesoscopic regime we would like to elucidate. And let's also tell this story within three-dimensional gravity. It allows me to draw nice pictures and also allows the calculations to be more explicit. So I will still give some pictorial way of describing what we're doing. So this is like a thermal correlation function. It's one which is regulated in a particularly convenient way. So instead of putting the density matrix right at the beginning, I sort of split the thermal density matrix between the operators. And also let us just consider autocorrelations, meaning the difference in space, the spatial separation between these insertions is 0. One can, of course, also do it for finite spatial separation, but that adds details that are not so interesting today. So if you just calculate this boundary two-point function with the black hole in the middle, that's the meaning of G beta. So I'm shaking the boundary and I'm asking what comes back. This calculation, I don't actually know who did it first, but it was first remarked famously by Maldacena that it takes this form, which actually decays exponentially at large times, and it decays exponentially forever at large time. It was pointed out by Maldacena that such a decay at very large time is actually incompatible with unitary quantum mechanics. And I think it's a similar statement, actually, that there has to be some fluctuation, some essential fluctuation that cannot die away at very large times. And I want you to keep in mind also this picture of the Brownian particle that came to rest, but still had to fluctuate because of the microscopic bombardment. Now, interestingly, so now this will have to swallow a bit. So let me say something about this computation. So I'm showing here only the boundary at first sight, which is a torus. The torus, because I'm on a finite system and I'm at finite temperature, I have two insertions of these operators, and the space-time, the ADS bulk, actually fills in this torus. So I'm asking what is the two-point function, which actually in some sense relates to geodesics in the space-time, where the boundary is one torus. And I get this answer. Now, by the same logic, I could have actually asked the following question. I could have said, well, what happens if I have actually two tori boundaries, and I have the same insertions on each boundary, and I look at two-point functions where I shake one or the other boundaries, and I ask what happens on one or the other boundary. So this I'm denoting as some kind of two-point function, which is G beta of T, G beta of S, calculated using the rules of ADS-CFT. And this is actually, these Euclidean spacetimes, we call them wormholes. In fact, in this particular case, they're Fuchsian wormholes with Wilson line insertions. And in a very similar context, they have been recently explored by these authors. Such a solution, such a saddle point of the gravitational path angle can be found for any operator insertions in this case, because we're always going to satisfy this condition. It's basically a condition that allows you to put a hyperbolic metric on it. And doing this calculation basically gives you an answer which has, like a 1 over cosh to some power times t, 1 over cosh to the power times s, times 1 over cosh to the power of t minus s. And this is already should already start reminding you of what we saw in this stochastic process. In fact, it has exactly the same functional structure. So what you see then is that this 2-point function, if you now want to know, in some sense, what is the expected fluctuation of the value of the 2-point function, you should look at large times t and s for t and s fixed, and you find that this also actually gives a contribution that doesn't vanish for large times. So what you find is you find the same structure of the Brownian particle, namely that its velocity seems to go to 0. It seems to come to a halt, which, by the way, also for the Brownian particle can be argued to be incompatible with thermodynamics. But if you actually look more closely, if you look at the actual erratic behavior of the trajectory, you find that there is a non-zero expectation of the fluctuation. And that's also the case here. So in other words, we should think of this, what this gravity calculation does, and I will back up why it does this. That will be the last part of my talk. Basically, that I should think of what I found to be the expectation with respect to some stochastic process, where the expectation gives you this exponential decay. But then if you look more closely and you actually ask about the fluctuations around this decay, you find that there's a part that will not decay as the times get large, but the separation between the times remains small. But what is interesting here is that the fluctuations of this mesoscopic correlator, we didn't actually impose them. We actually just applied the dictionary of the semi-classical pattern law, and we found nevertheless that these mesoscopic fluctuations are there. They're sort of built in. Now, what are they? So let me talk a couple of minutes about the perspective from this boundary CFT. So this theory that lives here on the boundary. And then I will conclude. So from the boundary perspective, well, in this 3-dimensional case, we're allowed with to work with a CFT that has 1 dimension less a CFT2. We want to work with CFTs that have a large central charge, basically a large number of local degrees of freedom, and that have a large gap between the vacuum and the black hole microstates. Above this gap, we have a Carty density of states. And you can actually convince yourself that the spectral width also scales with the central charge itself. And this spectral width is basically a way of estimating the size timescale of the fluctuation. Timescale of the fluctuation, EI minus EJ, will be always bounded by the spectral width. And it tells you that if you take a thermodynamic limit here with C large, then this actually does meet the criteria for a mesoscopic description. So now the correlation function of these light operators, we can write it now in CFT language. So we do these 2 operator insertions, we calculate them with respect to this CFT. What we can do is we can now explicitly see how these UV, these heavy black hole microstates, basically act as the, let's say, path that buffets around the gravity, semi-classical gravity part. So as it is the case in CFTs, you can expand these correlation functions in an OPE decomposition. There are 2 channels. People like to call this one the necklace channel, and this one, unimaginatively, the OPE channel. This looks a little bit like a necklace, I guess, if you drew the lines like this, something you could wear around your neck. But the channel that is actually now, so in our paper, we analyze both of these channels. The one that will be the most useful now is this OPE channel. And what I can write here is I can write the contribution from the identity operator, which has over the years been argued to essentially give you, well, shown to give you the predictions of classical gravity. This is what will give me just the 1-point function of this IR observer, plus a bunch of other contributions. So these are the so-called torus conformal blocks, plus a bunch of contributions which essentially come from the black hole microstates. And what we want to argue is that the average of these black hole microstates manifest themselves as the fluctuating contributions on top of this classical behavior. So, well, now we need to understand what is this ensemble of these OPE coefficients of heavy states. So that's part of what I talked about at the annual BHI conference, but let me just review it a little bit. So the ensemble for a 2D CFT should be basically a joint statistical model of the data for a 2D CFT. That means that the conformal dimensions, or left and right conformal dimensions, H and H bar, and the OPE coefficients should be themselves random variables, and we can fix the distribution of these random variables by imposing on this ensemble the so-called bootstrap constraints. And the max entropy or maximum ignorance ensemble consistent with these so-called bootstrap or crossing equations gives us a statistical model for, in particular, this OPE coefficients, which we can insert into this correlator. And what we find is, surprise, surprise, I guess otherwise I wouldn't be talking to you about it, that it gives the same one-point function, and it gives also exactly the same statistical correlation. You see, and this statistical correlation, it would have no business to be present in this CFT unless I argued for you, in this case mesoscopically, that I should be allowed to think of this as some kind of stochastic process or some kind of ensemble. So I expect that there are also exact agreement for higher and higher moments, but of course the geometric calculations get rapidly unwieldy. Even the CFT ensemble calculations get a bit unwieldy, but less so. So let me conclude. So basically, well, I started by giving you a more general introduction, but then I decided to talk about some more recent work, which is more specific. So we have this black hole Hilbert space. We have this number of microstates which satisfy some sort of property of, I like to call it, well, actually, one of my chaos collaborators likes to call it hard quantum chaos, meaning the random matrix description of the Hilbert space is maximally applicable. These are some states that we think of as being very heavy, that are typically unobserved for a low energy observer. And there is this very low energy sector, which is essentially what we think of as classical gravity. And I focused on some intermediate regimes, a meso regime between these two, where I can actually describe both the universal physics of classical gravity, as well as some of the fluctuation contributions that come from the microstates in this sense that I hope to have explained to you. So, so a certain class of these observables furnishes a mesoscopic intermediate regime, which I think is quite fascinating. Now, what do I want to do with this? Well, what is interesting is that there is a large theory of these mesoscopic stochastic processes, and typically one derives them or one specifies them using some Fokker-Planck or Langevin type equation. And those Fokker-Planck and Langevin equations are themselves associated to a whole theory of path integrals and effective actions. And so what I want to ask, and I of course have some kind of a guess what one might get, I want to ask what would be the path integral of this stochastic process that I just characterized for you in terms of a Wiener type path integral. And of course, what I think, so for the experts in the audience, I think this will be some sort of one-sided semi-classical gravity path integral, which gives you like a GKPW formula, but with random noise. So you can now actually get the correlation functions and the noise contributions, or let's say the mesoscopic scale of the noise contributions. So thank you for your attention. I think there's some time for questions then.
Oh, we have time for questions. Yeah, go ahead.
Is the statistical correlation suppressed relative to the reading?
Yeah, like in these formulae, you saw there was like a 1 over z squared, for example, for the fluctuation, 1 over the partition function squared.
So just to understand the analogy better, in Brown in motion, it's a Gaussian process. So the 1 point and 2 point function is all there is. All the higher moments are fixed.
That's right. That's not the case here.
And that's not the case.
It's like strongly non-Gaussian. I think I might have written that somewhere, but I decided to skip it in view of time. but we know that it's a strongly non-Gaussian. And so also when I say, for example, Wiener type, I mean, okay, I think here also the ones that are understood are of Gaussian type, ours will not be of Gaussian type.
Yeah, so in some sense, all these higher moments carry more and more information.
Yeah.
And so I'm asking, is there a distinction between Brownian motion where once you've measured the first and second, 1 and 2 point function, you learn nothing more and you don't learn about the microphysics?
Yeah.
Is it different for the black
I
hole?
think so, actually, and good, so I can somehow edit this out of the talk today. Tomorrow, I will talk about that in more detail. No, I will, because we will even comment about it in the abstract. In fact, what we're saying is in some sense that there are higher and higher moments which are present in the gravitational calculation. And this mesoscopic regime is kind of like a duality between all the moments and the stochastic process. But maybe, just maybe, it can be summed up into a whole thing, and that will be the meaning of this guy here. Yeah, and
Could you just summarize again what the range of the mesoscopic regime is, how you define that regime, and what is the parameter that tells you that this mesoscopic analysis is full there?
I think it's something like a square root of beta over c, and it comes from the fact that, so in general what you want is you want like there's like a microscopic scale, and you want the number of, let's say, processes that happen on this microscopic scale, you want it to be still large on the mesoscopic scale, but you want the mesoscopic scale still to be small compared to the macroscopic scale. And so now you need to estimate what is the fluctuation, what is the largest fluctuation that you can have in the system. And that is why I looked at the bandwidth, right? Because EI minus EJ can be at most delta E. And so if you actually look at delta E over E, you get something like beta over, oh, sorry, this should have been beta to the third. You get something like beta over square root C. So then maybe I said something one should be different power of beta, but it's basically a.
Wait, isn't that dimensional now?
Yep.
The power of beta.
Yeah. So I think one of them has the wrong power of beta, right?
Yeah, that one.
So mesoscopic is large E but small delta E squared. Is that how we should think of it?
But I want to think of it as a scaling limit of C and beta.
Yeah.
Together.
Such that you have high energy.
No, high C and high temperature. Yes, high energy, high C.
There's a moment when you,
Dimensional, right?
Hmm?
But what, that's not dimensional, right? Is there a dimensionless parameter?
Let me think about it.
there was a moment late in the presentation where you identify the necklace term, this one, and the OPE channel.
Yeah.
And then from here on, it's just OPE. Is that because they remain identical, or is it only for this special?
So we, in the paper, we do the analysis in both of them. It's just more, so in the CFT, the expansion in either channel gives you the same answer. But it's more transparent from this, like the fact that you can really isolate the UV physics from the IR physics is more transparent in this channel, which is why I've chosen it.
Okay.
No. Yeah.
So if I understand correctly, at some point you kind of traded well, so in Brownian motion, I think, and maybe correct me if I'm mistaken about it, but I think we sort of think that there's an ensemble of states, or in the classical theory, ensemble of configurations. That's what the expectation mode is about.
No, I think it's over time, right? It's really because you have like so many collisions on the scale that you observe the fluctuations. You have so many microscopic fluctuations that they are effectively randomized. So in fact, you don't really need an ensemble. That's actually one of the attractive things here.
Maybe I don't understand. I mean, I guess like, so let's say we have a box of gas and a particle moving in.
Yep.
If we knew the exact configuration of the particles in the box of gas, we get a specific trajectory of the particle and quantum physics, right? And so when we say expectation values, because we don't know which instantiation of the thermal state of the rest of the particles.
But yes, but there is more, yeah?
Yeah.
No, but go ahead with your question first.
Oh, no, nothing. So I guess, so the quantum version, we could say you pick a state out of the thermal ensemble, and then you compute the 2-point function, and then when you want to compute the expectation value of the square to give the variance, it's like you would take the square of that, and then average it over states drawn from the thermal ensemble. So that's no longer just the expectation value of thermal ensembles, it's quite a different.
Well, I think, no, I think it's slightly different, but you know, it's, if you have many truly microscopic UV collisions over this time scale, which let me call it the mesoscopic time scale, then you can say that these Brownian impulses are statistically truly independent, and they come from some actual statistical distribution that is the average over the microscopic scale over some mesoscopic scale. Okay, but these are really in the full system, those are subsequent, like, you know, linear collisions that happen. And it's the aggregate effect that gives you one of those, let's say, mesoscopic collisions. And those are statistically independent. And that allows you to write down the stochastic process. But you don't need an ensemble of the system. It's a system that makes its own ensemble. It's different. It's not a thermal ensemble, where you really have an ensemble of instantiations of the system.
I guess it depends on what you think is the input, right? If I took as the input the position of all the gas molecules at the beginning, I could recalculate the whole
You could.
principle, right?
Well, but I
Then
mean,
it won't be
again,
statistical
it would be very
rigorous.
difficult for you to do. And here we have a description that actually gets to some of these fluctuations without having to do that. That's somehow the point.
Maybe your picture is more like, let's say, especially in quantum mechanics. If you measure you have a specific microstate of the gas, and then you measure the position of the particle at some time steps, then of course you'll get a different set of answers each time because of quantum mechanics, and then that's the Brownian path.
I don't know, maybe let's talk about it without time.
I guess, yeah, let's maybe end here and thank Julian again.
Thank you.